So, today we will discuss compact sets in a general metric space that requires the concept of open cover. So, first we see open cover. By an open cover of a set, E, in a metric space X D, we mean a collection of open set, collection G alpha, where alpha belongs to the index set, omega of open subsets of X such that arbitrary union of these open set G alpha covers E when alpha belongs to omega. Okay. So, if an collection of the open set whose unions arbitrary union covers E, then we said this collection of the open sets in the metric X D is called an open cover for E. So, we define the compact set, a subset K of a metric space X D is said to be compact if every open cover of X, every open cover of K, every open cover of K contains a finite subcover. That is the meaning of this is, meaning is if G alpha is an open cover of K, then there are finitely many indices, alpha 1 say alpha 2 alpha n, such that the finite union of these sets G alpha 1, G alpha 2, G alpha n, finite union of these covers K. So, this set is said to be compact. So, it just like a compact set requires the finite number of the open sets which are responsible to cover the entire set. Suppose we have a security system in our IITs, and we are it's foolishness to apply the security point wise, means infinite number of people you just put it on the security, that is not a wise decision. So, what we do, we put up a check post, and then only finite number of check posts is basically is sufficient to look after the security. So, that way we say campus, the security system in the campus, that forms a compact sets. Okay. So, it is just like an arbitrary set E is said to be compact whenever any open cover of it has a finite subcover. That is, there are only finite number of open sets whose union will cover the entire set X. Obviously, finite set is a compact set. Every finite set is compact. there are infinite sets also which are compact. So, we will see that infinite compact sets in all case, we will see there are infinite sets which are also compact. Say just I take an example of a set of all the real numbers in the interval 0 1. It is an infinite sets, but it is compact, because only we can divide say 2 3 intervals we can choose such that the union will cover the whole interval a b. So, that will be we will see the others example for it. Now, one thing which we get that suppose E is a subset of y which is subset of x, and if E is open with respect to relative to y, relative to E is open relative to y, relative to y, that does not imply that E is open relative to x. It not necessarily that if a set is open in a subset submetric space by, because x t is a metric space, by is a subset of x. So, by d will also be a metric space. So, if a set is open with respect to the metric space by d, then it may or may not remain open with respect to the metric x. And examples we have seen the R 1 and R 2, an open interval a b is open in R 1, but not in R 2, is it not? So, the openness or the closeness of a set depends under which the set is embedded, but this is not the case so far we consider the compactness. If a set is compact relative to the y, then it has to be compact relative to x and vice versa. So, this is an interesting result for the we have this result as follows. Suppose K is a subset of y which is a subset of x, where x d is a metric space, is a metric space. The result says K is compact, relative to x if and only if K is compact relative to y. So, let us see the proof of this. So, what we want is that if K is compact with respect to y, then it has to be compact with respect to x and vice versa. So, let us suppose K is compact, relative to with respect to or relative to x. It means, if we choose a collection of the open set which are relative to x, those countable union covers K, then there will be a finite subset, a finite collection of those open set which can cover K. This every open cover of K in X will have a finite cover. So, this is known. We wanted to show K is compact relative to y. So, let us consider the open cover of K with respect to y or relative to y. So, let V alpha be a collection of sets open relative to y. Now, prior to this we have one result. We know the result says suppose Y is subset of a metric space X, a subset E of Y is open relative to Y if and only if there is a if and only if E can be written as by intersection G for some open subset G of X. This result we have already shown. Okay. So, using this result, we can say if B alpha is given to be an open relative to Y. So, according to this result, B alpha can be expressed as by intersection G alpha for some open subset G alpha of X. So, we can say that they are all these sets. So, they are all sets say G alpha open relative to Y, relative to X such that V alpha is nothing but the Y intersection G alpha for all alpha. Means V1 will be Y intersection G1, V2 will be, so correspondingly we can get the open sets G1, G2, Gn relative to X. Okay. Now, what is given is K is compact relative to X. So, G alpha is an open set relative to X. So, this collection of this open cover will have a finite subcover. So, since K is compact relative to X, so there are, so K will be contained in the finite union of these open sets G alpha 1, G alpha 2, G alpha n. Okay, for some choice of finitely many indices, for some choice of indices, finite indices alpha 1, alpha 2, alpha n. Okay, like this. Now, if I take, since K is contained in since K is a subset of X, K is contained in Y, this is given. This is given, K is a subset of Y, K is contained in Y. So, K is contained in Y. So, this implies that K, which is K intersection Y, is contained in G alpha 1 union G alpha 2 union G alpha n intersection Y, and that is the same as this, that union of G alpha I intersection Y, where I is say 1 to n. Okay. But G alpha I intersection Y is nothing but V alpha, is it not? So, this is the same as the union V alpha 1 union V alpha 2 union V alpha n. So, K is contained in this union, that is the finite number of the open subsets relative to Y covers K. This shows K is compact relative to Y. K is compact relative to Y. Now, conversely, suppose K is compact relative to Y. Relative to Y. We wanted to show K is compact relative to X. So, let G alpha be an open cover of X. We open subsets of X which covers K. it is an open cover, covers X, okay, which covers K, sorry, because K is compact with respect to which covers K. Okay. K is compact with respect to Y. What we are doing is, we wanted to show K is compact with respect to X. So, let us find out an open cover G alpha of K. Now, if we prove that this open cover, which is an open cover, which are the open sets with respect to X and covers K, if it has a finite subcover, then obviously K will be compact with respect to X. Okay. So, let us put the put V alpha as the set by intersection G alpha. Okay. Y is a subset of X, G alpha is an open set. So, this V alpha will be open set relative to Y, because of the previous result. Okay. Now, this is given K is compact related to Y. So, since K is compact relative to Y, so this open cover of V alpha has a finite subcover. So, there exist alpha 1, alpha 2, alpha n such that the union of these V alpha 1, V alpha 2, V alpha n covers K. Okay. But B alpha 1, B alpha 2, B alpha n, these are the subsets of what? Subsets of G alpha 1 union G alpha 2 union G alpha n. B alpha 1 is a subset of G alpha 1, B alpha n is a subset of G alpha n. So, K is also contained in the finite union of these open subsets which are open with respect to X. Therefore, every open cover of X K relative to X have a finite subcover. So, this implies K is compact relative to X, and that proves the result. Okay. Now, another result shows that closed subset, compact subset, the compact subset of a metric space spaces are closed. Every compact subset of metric space will be a closed set. Whatever the metric may be, is an arbitrary metric space. Every compact subset is a closed set. Let us see the proof. This we will prove by contradiction. Suppose K be a compact subset of X, K be a compact subset of X D of a matrix. So, in order to show K is closed, if I prove its complement is open subset of X, then is okay. So, in order to prove, required to prove is K is closed. So, what we do is, we will prove that its complement Kc, complement of K, this is an open subset of X, So, here we have, this is our metric space, this is a set K. What we want is the complement of this Kc is open with respect to X. So, it means if I take any point here, say P, which does not belongs to K, and if we are able to show there exists a neighborhood around the point P which is totally contained in Kc, then obviously this point P will be an interior point of Kc, but P is an arbitrary. So, we can say every point along of Kc we can draw the neighborhood which is totally contained in Kc. So, Kc becomes open. So, that is the idea of the proof. So, let us take, suppose P is a point belonging to a complement of K, that is Kc. Okay. but that is in x, or you can say p, that is p is in x, but p is not in k. That is the meaning of this. P is in x, but it is not in k. Now, let us take a point q. If q belongs to k, then there is a distance between p and q. So, this is the distance between p q. The distance of this is nothing but the d of p q. So, if I take a radius less than half of the distance of p q and draw the neighborhood around these points like this, draw the neighborhood around this point like this, then this neighborhood will be disjoints. So, let this neighborhood be denoted by b q and this neighborhood we denote by w q. So, let us take this let v p b q and w q be neighborhoods of p, and q respectively, b and q, p q respectively, of radius less than half the distance between p q. Okay. Then obviously, that v q intersection w q will be empty, disjoints, that is true. Okay. Now, let us take, since k is compact, k is given to be compact, is a compact, k is compact subsets of metric space x t. So, every open cover of k will have a finite cover. So, there are all the points q 1, q 2 in q such that the open ball drawn at q 1, q 2, q n, finite number of open ball will be sufficient to cover k. So, let us say there are finitely, so there are finitely many points, say q 1, q 2, q n, k 1, q 2 in k, such that the open balls or neighborhood drawn at this point with a radius half of q 1 p etcetera will remain, such that the neighborhood drawn at these points with a radius I will say after. So, w q 2 union w q n, where the radius of w say q I is half of the distance from p to q I. Okay. Now, this finite number of these neighborhood will cover k, because k is compact. Okay. Now, since these neighborhoods you are drawing, this is our k, here is q 1, q 2, say q n, here is p. So, what we are doing is, we are drawing a ball, say this ball, okay, and here it say this ball. So, here it is w q 1, this is nothing but v q 1, which are disjoint. Then we are taking say q 2. So, again p 2 we are taking, say this is our say v q 2, and here it is say w q 2. Again they are disjoint, because the distance does not match, does not is less than half of the radius is less than half of p of q 2, So, obviously, there these B q 1, B q 2, B q n will be disjoint with that. Okay. So, let if so V q 1 V q I intersection W q I is empty. Okay. That is. So, if we take V as finite union of V q 1, V q 2, V q n, suppose this finite union, then this will be a neighborhood, is a neighborhood of P, is a neighborhood of P, and this neighborhood does not intersect, which does not intersect with W, which is W means W q 1 union W q 2 union this one say W q n, W q n. This does not intersect with this, because this is the smallest one which is disjoint with everyone. So, we have a totally a neighborhood. So, this implies that this neighborhood V is totally contained in the complement part of K. Therefore, P is an interior point of K complement, but P is an arbitrary point. So, this shows that interior of this is an open set in X T. So, once it is open, then K must be closed. So, every compact subset of a metric space is a closed set, and that is what we prove.